We're going to start with the speaker again. The cone's moving back and forth, and so it's sending compressions, it's sending disturbances out toward the room. But you don't hear it, and the reason you don't hear it is because of the frequency. Think about the cycles per second, the number of compressions per second, and that is determined by the speaker itself, the thing which is causing the disturbance. And you don't hear it because this is oscillating back and forth at 1 hertz, 1 cycle per second. So 1 cycle per second, you don't hear. If I go to 10 cycles per second, the motion's a lot faster. It's almost too fast to see. And I'm starting to hear the puffs of air which come off that, but I'm not quite hearing the tone. But if I turn it up to 100 cycles per second, that you hear. As a matter of fact, I have to turn down the amplitude so that you can hear me over top of it. Now this cone is still going back and forth. It is still sending out the compressions, but it's doing it at a frequency that your ears are sensitive to. That's 100 cycles per second. And it turns out you're more sensitive to 1,000 cycles per second. That sounds slightly louder. And I'm going to turn down the amplitude a bit more. And let's look at the upper end of your hearing. If I increase the frequency, you can still hear it, but at a certain point, it goes off the range at which your ears are sensitive. This is still vibrating. It's still making sound, but you can't hear it. It's beyond the threshold of your hearing. In the book, there's a table that shows the range of hearing of different animals. And as you might suspect, big animals tend to be sensitive to lower frequencies. Smaller animals tend to be sensitive to higher frequencies. And that's a function of the size of the structures that detect the sound waves. The next property of waves we'll consider is speed. If I shake a disturbance in this wave machine, it travels with a certain speed. So think about the speed with which the disturbance travels. Now the speed is a property of the medium. This wave machine has a certain speed. If I shake a small wave or I shake a big wave, they travel at the same speed. Same thing with the sound that comes out of the speaker. High frequencies, low frequencies, loud sounds, quiet sounds all travel at the same speed. It's a property of the medium. For sound waves, it's a property of the temperature and the gas. But at room temperature, in air, we have a particular speed of sound which we use, which will work for most of the calculations that we do. But there's one other wave property we want to look at, and mostly we're going to consider sinusoidal waves. So they're produced by systems in simple harmonic motion. And so I'm not going to have just one wave, I'm going to have one wave after another. So I'll have something more like this. And if I do that, I produce a so-called sinusoidal wave, okay? And for a sinusoidal wave, we can consider one more aspect, and that's the wavelength. What's the distance between successive crests of the wave? So let me shake a couple of crests on here. So that distance between two crests or between two troughs is the wavelength. So we've seen 3 properties that describe waves. There's the speed, there's the frequency, and there's the wavelength. But it turns out they're related. And let's see why. I'm going to shake 2 successive waves on the wave machine. The distance between them is the wavelength. The time between them is the period, okay? The speed is the speed with which the whole thing moves. And there's a relationship between them, and let's see why. I'm going to shake 2 successive waves. We're going to mark the wavelength. We're going to watch it travel at a particular speed, and the period is going to be the time between them. And we can measure the time between them by looking at their arrival at this end. So let's try that. Okay. So the wave is moving at a particular speed. The wavelength is the distance between the successive crests. And the period is the time between the arrival of the crests at the opposite end. Now suppose I shake the wave more quickly. So I do 2 crests that are closer together. It's a shorter period, but it's also a shorter wavelength. Let's try that. Shorter wavelength, also a shorter time between arrival of the crests at the opposite end of the wave machine. And so you can see as the wavelength gets shorter, the period gets shorter as well. And so as the wavelength gets shorter, the frequency gets bigger. And so there's a fundamental relationship that we'll have for sinusoidal waves. And this is presented in the chapter, and we'll use this to solve a wide variety of problems. And in fact, we're going to give you a chance to solve a problem right now. Okay, we're back to a sound wave. And right now, the speaker It's oscillating at 100 hertz. So it's sending out 100 pulses per second, 100 waves per second, headed out into the room. So think about the wavelength, the distance between successive crests. I'm going to take the signal generator and I'm going to turn it to 1,000 cycles a second. So instead of sending out 100 crests per second, it's sending out 1,000 crests per second. And when I do that, how will the wavelength change? Frequency goes from 100 to 1,000. The wavelength, how is that going to change? We'll give you some choices. Okay, let's take the signal generator and turn it from 100 to 1,000. And when I do that, you can hear it a lot better. Your ears are much more sensitive in this range. But this is oscillating much more quickly. So think about this. As each pulse is created, it travels outward, but they're being created more frequently, and so they're closer together. The wavelength is shorter, and that's also a match for this fundamental relationship for sinusoidal waves that we have. Now there's one more aspect of waves we want to consider, and that's a question of energy and intensity. All waves carry energy. And for sound waves, you're sensitive to that. I can have sounds which are louder or sounds which are quieter. And we want to talk about different ways to measure that, different ways to quantify that. And we'll talk about that in the next segment.